So let's review a little more series parallel combination circuits by looking at a typical ladder diagram or ladder network. So in order to do this, we're going to use the reduce and return method and look at all of the voltages and currents in this circuit. Now in our ladder circuit problem, let's work on the reduce and return method here. So the first thing I'm going to do is we will combine our 5 and our 6. These are in series, so we're just going to add those together and we get our 3 ohm resistor here in our next step. And then it looks like we now have a 6 and a 3 ohm resistor in parallel, so we're going to combine those and we get this 2 ohm resistor right here that is now in series with our 4 ohm resistor. And if I'm going too fast, just pause the video and see if you can work through this yourself with me. So we combine those by adding them because they're in series, and we get this 6 ohm resistor right here. Then we have a 6 ohm and a 6 ohm in parallel. When we have 2 resistors in parallel that are the same, the new resistor will be half the original resistance. We have a 3 ohm resistor there. And our final combination is our 5 and our 3 to make a total of 8 ohms, and that is our total resistance of our ladder circuit. Once we find this, what we want to do is find our source current, which will be the 240 volts divided by 8 ohms, and that tells us that we have 30 amps of current coming from the source. So that's all we can do with that last step, and we're just going to step right up and return back to the next one. So what we found there was that we have 30 amps coming from the source, and that's going to allow us to find our voltage drops. So the voltage drop across the 5 ohm resistor is going to be our 30 amps times 5 ohms. So we have 150 volts there. And the voltage drop across this 3 ohm resistor is 30 amps times 3 ohms, or 90 volts. Okay, so far so good. So we're just going to step up to the next level and add what we've learned here, which is that we have 30 amps coming from the source. We have 150 volts here. The 90 volts here is across a 3 ohm resistor. Well, that 3 ohm resistor is actually the combination of 2 parallel resistors, and parallel resistors have what? The same voltage. So each of these should be 90 volts. And now that allows us to find our currents. So 90 volts divided by 6 ohms. That means that we have 15 amps, and they're both 6 ohm resistors, so that's 15 amps through each, and that's all we can do there. So we go up to the next level and transfer everything we know. We have 30 amps coming from the source, 15 amps here, 15 amps here, and then I'm going to write in our voltages, and we know we have 90 here because that didn't change. Now from here, this 6 ohm resistor is the combination of 2 series resistors, which actually divide our voltage. So how are we going to find the voltages across each? Well, we have the current, so we are going to use the current to find the voltage drop across the 4 ohm resistor and across the 2 ohm resistor. Same current through each because they are in series with each other. 60 volts and 30 volts there. Again, I'm going to go up and transfer what we've learned. So we have 30 amps here, 15 amps here, 15 amps here, 150 volts here, 90 volts here, 60, and 30 volts here, because remember the 2 ohm resistor was the combination of my 6 and my 2 in parallel, so they're both going to have 30 volts across there. And the current through the 6 ohm is going to be 30 volts divided by 6, or 5 amps. And the current through the 3 ohm will be that same 30 volts, this time across 3 ohms of resistance. So I have 5 amps there and 10 amps there. So as you can see, your 30 amps coming from the source, it splits evenly here, but not evenly here, because we have different amounts of resistance through those branches of our current divider. So I'm just going to transfer everything back up to the original circuit, and we're almost finished. Write in all the currents. And then we've got 5 amps here, 10 amps here. We have 150 volts here, 90 volts here, 60, 30. Okay, so the 3 ohm resistor down here in part 2 is split between the 1 ohm and the 2 ohm in the original circuit. So how we're going to find the voltage there is that we're going to multiply the current through the resistor times the resistor value. So I should have 10 volts here, and V6, 10 amps through 2 ohms of resistance is 20 volts. Okay, and a quick check here, we had 30 volts down here, and that is now split between 2 resistors, and we have 10 and 20, so that works. You can do these quick little checks and make sure that you see what's going on. But what ladder networks tend to do is there's some current coming from the source, and that current splits in some proportion at the first junction, and then a portion of that current splits again, and so on, the more branches you have. So that's a good practice problem for our series parallel. Now let's talk about loading and unloading of a voltage divider. We talked before about how a divider circuit is series resistors. So in this case, if I have a 10 ohm, a 20 ohm, and a 30 ohm resistor in series with my 120 volt source, I should see 120 volts here at this point with respect to ground, and then I should see 100 volts here, because we should have a 20 volt drop there. And then we should have a 40 volt drop across the 20 ohm resistor, so we'll see 60 volts here, and then a drop of that 60 volts across the 30 ohm resistor. So if you want to prove this to yourself, you can pause the video and work through it. Again, these are just meter measurements. These are not, this is not a circuit of any sort out here, so we're just measuring what voltages should be there under no load conditions. That means we don't have anything connected to A, B, C at this point. Now, what happens when we put something out here on point A and point B and point C? Well, they're going to have some resistance to them. And let's work through this and see what our voltages are at B and C in particular. We're going to have 120 volts here no matter what, because that's actually in parallel with our source. But let's look at see what happens at B and at C. So in our loaded voltage divider circuit, let's treat this as we would any other series parallel circuit and use reduce and return. And we're going to combine the R3 and the load resistor in parallel. That gives us a 12 ohm resistor. We're going to combine that with our 20 ohm resistor in series. Then combine the 32 and the 20. The 10 and the 12.3. And then in our last step, we'll combine our 2 parallel resistors, and this is where we end up. So, using Ohm's law, we find that We have 11.37 amps here. That's just your 120 volts divided by the 10.55 ohms. Step up to the next step. We have that 11.37 amperes here. And the 10.55 ohm resistor is now split into two parallel resistors, and those are both in parallel with the source, which means they have 120 volts across each of them. So using Ohm's law, 100 divided by 22.31, 5.38 amps. 120 divided by 20, 6 amps. And check as you go through. We've got 11.37 amps coming in, 5.38 leaving, and 6 leaving. That's very close to equal. Probably a rounding error in there somewhere. Okay, up to the next step, and we're going to add back what we have learned. 11.37 amperes here. We have 5.38 amperes on this branch and 6 on this branch. We still have 120 volts here. That 20 ohm resistor did not change. However, we want to find our voltage drops here and here. So we're going to take our 5.38 times 10, and that's our voltage drop there, and our 5.38 times 12.31 to get our 66.23 volts here. So we had 120 volts across both of these in the previous step, so those should add up to 120 as well. So we go up to the next step and transfer everything over again. 11.37 amps here, our 5.38 amps here, 6 amps here. We still have our 120 volts here, and the 66.23 is now the same voltage drop across each of these parallel branches, which will allow us to find our current. 66.23 divided by 32 ohms gives us our 2.07 here, and 66.23 volts divided by 20 gives us 3.31 amps here, which should add up to the plus the 2.07 to the 5.38. So that 5 amps is coming in and splitting between those branches. We'll go back one more level. We have our 11.37 amps here. We still have 5.38 amps here, or 3.31, 2.07 amps. We still have 120 volts out here. This didn't change either. Now we need the voltage drops across our 20 and our 12. So 20 times 2.07 is 41.4, and 2.07 times 12, 24.84 volts. Okay, well, the final level right here, we're just going to transfer everything we've learned up to this point. And then our voltages. We found our voltage here before, and here, oops. Oops, that's 41.4. And here was 24.84. And that's also going to be the same voltage drop over here with the parallel resistor, which should allow us to find our current. So 0.83 amps here and 1.24 amps here, which adds up to our 2.07. Now the reason I wanted to do this was, remember what we had before was we had our 120 volts here, we had 100 volts here, and we had our 60 volts here for our divider. Now what we actually have, because I'm going to cross these out, actually we still do have the 120 volts here, right? Because it's still in parallel with the source. However, notice here, instead of having the 100 volts we were looking for, we actually have 120 minus 53.8, which is about 66 volts. And here we actually have our 66 volts minus the 41.4, which is about 24 or 25 volts. So as you can see, that's very significant drop from what we hope to have, simply because of these load resistors. So stay tuned and I'll show you how we can fix that. And as you can see, it looks like we do have here about 66 volts, and that should have been 100 volts if this were unloaded. And down here we should have had about 60 volts left, again under the no load conditions. So as you can see, when we put a load out here, it matters significantly. It can change how much voltage we're supplying to these circuits. However, there's a good fix for this, and that is if we, instead of using a resistor that's very close in value to our divider circuit resistors, if instead we use a very large resistor out here, so make sure that the load has a lot of resistance versus the resistance of the divider circuit. As you can see, we get very close to our original values. We're at 99.9 volts here, which is very close to the 100 that we had before, and we're at 59.9 volts here, so we're very close to that 60 volts that we wanted to see before. So again, just wanted to make you aware that if your load of your voltage divider is not much greater in terms of resistance than your divider resistors, you're going to see a different voltage from what you're looking for. So keep that in mind. So let's move on to something new, something that you haven't seen before. Source conversion. We've talked in Circuits 1 all about voltage sources, but now we're going to introduce you to current sources. Current sources are described as the dual of the voltage source. And just as a battery provides a fixed voltage to a network, a current source establishes a fixed current in the branch where it's located. So you don't see very many current sources you won't see them in our lab. However, they appear extensively in the modeling of electronic devices such as the transistor. And you'll get to that when you get to analog devices. So what do I mean by this? Well, instead of a voltage source here, we have a current source. And what this means is this 10 milliamps is the current through this branch. And since that's the current through V1 through R1, that's going to determine our voltage drop. So I1 is also 10 milliamps because it's in that same branch. 10 milliamps through a 20 kilo ohm resistor means we have 200 volts across that resistor. And since that's in parallel with our current source, that means that our source voltage is 200 volts. So you might have to start thinking a little bit backwards from what we did before. Remember, we used to reduce circuits down so that we could find their source current. Now we might be reducing them to find the source voltage. So let's look at this example, for instance. So we have 7 amps coming from this source, and that 7 amps is in this branch right here. We have a 12 volt voltage source, and we have a resistor over here. And we're looking to find what is I1 and what is I2, and what is the voltage drop across my current source. Well, the voltage drop across the current source is fairly simple. It's in parallel with this voltage source. We know that because they're connected on this side and they're connected on this side. That means we have to have 12 volts here. Also, we would have 12 volts across our 4 ohm resistor, because again, the 4 ohm resistor is also in parallel with the voltage source, and we have to have the same voltage across parallel branches. So we have a 12 volts across the resistor here, and 12 volts divided by 4 means the current has to be 3 amps through the 4 ohm resistor. Now, how do we find I1? If we have 7 amps coming into this node, or this point where these wires come together, and we have 3 amps leaving, what would that make this current right here? Did you say 4 amps? Yes. Okay. 7 amps coming in means we have to have 3 leaving and 4 leaving this way. And let's look at another example of using a current source in our circuit. So here we've got a 6 amp source supplying this current divider. It's a current divider because these resistors are in parallel, and parallel resistors are a current divider. Okay, so I'm going to introduce you to, actually no, we're not going to do the new equation just yet, but remember the current divider rule says that the total resistance divided by the resistance of this path times the current coming in gives you the current through that path. So if we use the current divider rule, we see that we have 2 amps through our 2 ohm resistor and 1 amp through our 1 ohm resistor. I'm sorry, 4 amps through the 1 ohm resistor. I thought that wasn't right. We should have less current through the greater resistor. And those 2 and the 4 amps come together on the other side. Now this 20 volts, this is not an open circuit. This is just telling you there's something else going on outside of the rest of this circuit, and we're telling you there's 20 volts here. So we want to know the voltage drop across our source, and we know there's 0 volts over here because of the ground node. So what is the voltage drop across here? Well, if we know we have 20 here, if we can find the voltage rise from here to here, we can add that to 20 and get our voltage right here. So V1 is going to be 2 amps that's going through R1 times 2 ohms of R1, so that has to be 4 volts. And let's check this. This is in parallel with R2, so they should have the same voltage drop. And I2 is 4 amps, so 4 amps times 1 ohm is also 4 volts. So we've got 4 volts across each of our resistors. That makes sense. So if we take our 20 volts and add our 4, that means the voltage drop across our current source is actually 24 volts. Now sometimes it's useful to convert a voltage source to a current source, or a current source to a voltage source, depending on what else is going on in the circuit. If we have multiple sources, sometimes it's helpful to do this. Turns out it's very easy to do this. Most voltage sources have a series resistance. That is the actual internal resistance of the voltage source. And current sources are modeled with a parallel resistance. So you have to have either a series resistor with the voltage source or a parallel resistor with the current source in order to make this source conversion. So let's see how this works. This voltage source is equivalent to this current source. The series resistor becomes the parallel resistor for the current source, and the voltage divided by the resistance becomes the current source. Or if you're going back the other way, the current times the resistance becomes the voltage source. Okay? So, now keep in mind, when we make this conversion, if I convert this to its equivalent current source, we have to have the same voltage and current across the load. Okay, that's otherwise they're not equivalent sources. They're only equivalent sources if they give us the same output, right? So let's look at our example here. What would our load current be for this 4 ohm resistor based on our voltage source? Well, this looks like just a series circuit right now. So if we have a 2 ohm resistor plus a 4 ohm resistor, we have a total of 6 ohms, right? And 6 volts divided by 6 ohms means we have 1 amp of current coming from the source. And since this is a series circuit, I sub L would just be 1 amp. I might have said ohm, 1 amp. And then 1 amp times 4, that's 4 volts. So if we convert that 6 volt source to a current source, we have to still have 1 amp of current through the 4 ohm resistor and 4 volts across it. So here is our equivalent current source. We get that by taking the 6 volts and divided by 2. That's just Ohm's law, right? I is equal to E over R. So 6 divided by 2 is 3 amps, and then we need that 2 ohm resistor right here in parallel. So again, your voltage source has a series parallel and your current source has a parallel resistor. Okay, so now our equivalent current source is a 3 amp source in parallel with a 2 ohm resistor and the 4 ohm resistor. Okay, you might have noticed the A and the B. What we did was we marked the terminals where that voltage source was, took it off, and then put our current source right back. Now I'm going to show you a new current divider equation that you might find useful, especially when we get to working these problems in AC. So this basically, if you have 2 branches, you can, and you're looking for this current right here, you would take this other resistor, the opposite resistor, and put that on the top of your fraction, and then divide by the sum of the 2, okay? And then multiply by the current coming in. It's an odd little equation, but it's going to be really powerful and helpful for you if you can learn this equation. Okay, so we're looking for this current here through the 4 ohm resistor. So we take 2 and put that above 2 plus 4, which is 6, and multiply that by the current coming in, which is 3, and we see that that would indeed be the 1 amp. If we multiply 1 by 4, we still get the 4 volts. One thing to note, this equation only works for 2 branches. If you try to use it for 3, it's not going to work quite the same. So when you have 2 branches, it will save you some time and some calculation. You don't have to calculate the total resistance first. All right, so why would we do source conversions? Well, look at an example like this. For instance, we have a current source on the left-hand side, on this left-hand circuit. We have a current source and a voltage source. Well, if we convert the current source to a voltage source, we get this, right? So 4 times 3 is 12. Notice it is oriented so that the positive side is down and the negative is up. That's because the positive side needs to be where the arrow is for the current source. So if the current is forced down, that's coming from that positive terminal. If the current source is facing up, that means the positive terminal is on the top. And then this 3 ohm parallel resistor for the current source becomes a 3 ohm series resistor for the voltage source. Most important thing to remember, voltage source has a series resistor, the current source has a parallel resistor. Okay, keep that in mind. Now when we removed this current source and replaced it with a voltage source, look what happened. We now have a series circuit with 2 voltage sources, and you probably remember from circuits 1 that we can combine those. So we've got the 12 volt source here and the 5 volt source here. That's 17 volts. Looks like they're facing the same direction. Divided by 5 would give you your current. So that's one reason we might want to do a source conversion. Now, we found that voltage sources cannot be placed in parallel. We talked about that last time. Current sources cannot be placed in series. Why? Because if you have 1 amp through one branch of your circuit, you can't then have two amps through. So they have to be, current sources can be placed in parallel, just as voltage sources can be placed in series, but current sources cannot be placed in series with each other unless they're exactly the same amount. Okay, so what happens when we have current sources in parallel? Well, just like our voltage sources in series, these can be combined. So if we have 6 amps pushing current in the upward direction and this current source forcing current in the opposite direction, what do you think the net current supply would be for the circuit? 6 up and 10 down would be a net of 4 down. If you said 4, you're correct. What about this one? We have 7 amps going up, 3 amps going down, and 4 amps going up. What do you think if we combined those three, what would our net current source look like? What direction and how much? And if you said 8 up, you are correct. Very good. Now again, here's another example where we might want to replace our voltage source with a current source, because why? We can combine the current sources in parallel at that point, and we can go from 2 sources in our circuit to just 1. So what would our current source look like if we replaced this voltage source with the current source? Well, Ohm's law tells us 32 divided by 8 is a 4 amp source, and it's going to be pointing up because that's where that plus, the positive terminal of the battery is. And this 8 ohm resistor is going to have to be in parallel. So there's our new current source. Now we can combine our current sources. 4 up and 6 up gives us 10. And then it looks like we combined our 8 and our 24 to be 6 ohms. So we reduced our circuit to a manageable, simple circuit to work. And that gives us 3 amps using our new current divider formula. Just remember, never put current sources in series, however we can combine them in parallel. If you need to, go back through this this PowerPoint and then start working on your homework.